We're in section 8.3, Semiconductor Junctions. When P-type material meets N-type material within a single silicon crystal, a P-N junction is formed. And so here we have P and N material, and this area right here is the area we're referring to as the P-N junction. The P-N junction is formed in the process of creating the semiconductor device. And we want to look at this junction in what we'll call an unbiased condition, and meaning that there's no voltage across it. Before carrier migration, there are equal numbers of holes and electrons on either side of the junction, and this results in a net charge of 0. Because of random thermal energy, some electrons will pass across the P-N junction, mating with holes on the other side. And this is referred to as recombination, and your text has a picture depicting recombination. I'm just going to draw a picture here, and we'll say this is P material and this is N material. And remember that P material has an excess of holes, and N material has the donor electrons, so it has extra electrons. Now, right at the point of the junction, and this won't be throughout all of it, this is just right at the point where these two materials are touching each other, there's going to be something interesting that occurs. Now, before they're put together, remember that the net charge is 0 volts. There is no charge on either of these materials. Now, when we bring them together, something occurs. The electrons here, now these are free electrons, remember, they see that available hole over there. And so the free electrons are going to move over to those holes. Now what that is going to do is, since this material on the N side is losing an electron, this will result in a net positive charge on the N material. The holes over here, which were net charge of 0, suddenly they received an electron, and now they have a net negative charge. And so we're going to have this region develop that has a net charge, and we're going to have a name for it. The end result of recombination is the creation of here it is, the depletion region, which means an area depleted of carriers. Well, what's that mean? The free electrons in the N material have filled the holes in the P material. And that's what we were talking about right here, that the free electrons moved over to the P material. Because the N material lost an electron, it now has a net positive charge. Because the P material gained an electron, it now has a net negative charge. But in this region, it is now depleted of carriers, because these, right in the area of this junction, those electrons that were able to move did move, and the holes which are able to serve as transport for electrons, they're all full of electrons. So we have a region that is depleted of carriers, and it actually has a potential voltage across it. After a time, the region will be depleted of charge carriers because of the migration of electrons and holes. This leaves an area known as the depletion region of the P-N junction. Further electron migration will not take place until the barrier potential is overcome. And so that region, that barrier potential, there is actually a voltage there. Now there's that difference of potential, and to overcome that, it will take 0.6 to 0.7 volts in silicon, and if it's germanium, it'll take 0.2 to 0.3 volts. And if you work with diodes, you'll find that there will be no current flow in this until you have overcome this barrier potential. So if you were to connect a power supply down here, you'd have to have at least 0.7 volts to cause this to conduct. Okay, the forward bias junction. An external source can either oppose or aid the barrier potential. If the positive side of the voltage is connected to the p-type material and the negative side to the n-type material, then the junction is said to be forward biased. Okay, forward bias. And so what we'll have here, notice, remember we had the free electrons in the n material and we had the holes over here in the p material. Now let's look at what's going to occur if we connect the battery like this. Notice the negative, remember current flows from negative to positive, and so here we have this negative force connected here, and we have these free electrons. Now these free electrons want nothing better than to move over to the positive terminal here. So they will, when it's connected like this, those negative electrons, those electrons that are negative will be forced to move through the n material, and most of them will move through holes through the p material, and they'll come over here. And the positive force here, the positive on this, remember the holes want to move from positive to now. Remember the holes are not moving anywhere, but this positive force will facilitate the whole process, causing electrons to move through the p material, and this will cause the depletion region to narrow drastically. And so this is a forward bias junction, and current will flow easily through this junction. Now let's talk about it a little more. In a forward bias junction, the following conditions exist. Forward bias overcomes the barrier potential. The electrostatic field created by the barrier potential had stopped electron migration. Now that was initially, that electrostatic field created the barrier potential and stopped electron migration. Now, a voltage of 0.7 volts, if this is a silicon, will overcome that barrier. Forward bias narrows the depletion region. Forward bias forces the majority carriers in both materials towards each other, thus narrowing the depletion region. We just discussed that. There is maximum current flow with forward bias. The power supply provides an abundance of free electrons and overcomes the barrier potential. Electrons move as conduction band electrons in the n material and as valence band electrons in the p material. When forward biased, the p-n junction resembles a short circuit. Okay, a reverse bias junction. Reverse bias occurs when the negative source is connected to the p-type material. Okay, negative is connected to the p-type material, and the positive source is connected to the n-type material. Now, reverse bias will have the effect of strengthening the barrier potential. Reverse bias widens the depletion region, and current flow is minimum at best. Now, what's going to happen here is, remember, in the n-type material we have these electrons, and these free electrons that want to, well, let's see, what do they want to do under this condition? They've got a power supply connected here, and the positive terminals here. Now remember, those electrons want to go to the positive side of the power supply. So what we're going to end up doing is in this region here, in fact all the way across this material, we are depleting this of electrons. So electrons are going to be pulling away from this barrier towards this positive force. Now again, the holes aren't going anywhere, but remember, hole movement would be from positive to negative, and so the holes are going to tend to want to move in this direction, and that will thus inhibit electron flow as well. So with reverse bias, we are going to cause a depletion of electrons in this region, and thus we will effectively shut this junction off. Okay, more discussion about reverse bias. A reverse bias junction has zero current flow, and that is ideally. Reverse current is temperature dependent. The higher the temperature, the greater the probability for reverse current. If reverse bias is increased enough, the reverse current increases dramatically, causing the PN junction to break down. This is referred to as junction breakdown. The voltage required to reach this point is referred to as the reverse breakdown voltage, RVB, and this is usually specified on data sheets, and this is something to be avoided. As the breakdown occurs, avalanche may occur and destroy the device if uncontrolled. Now, most PN junctions are designed to not operate in a reverse bias junction, a reverse bias condition. There are a few devices like Zener diodes that actually do operate in reverse breakdown, but for most devices, if they go into junction breakdown, you're looking at destruction of the device. So, in this section we have looked at PN junctions, we looked at reverse biasing, we looked at forward biasing, we looked at the unbiased junction, and that concludes 8.3.